Stanford University.
Oh, we're on. Welcome to the last talk of the quarter for AA380. Please remember to send in your comments on all talks and complete the evaluation forms by March 20th. As you can see on the website, some very interesting talks are starting to appear on next quarter's schedule, and the first talk of the quarter is likely to be standing room only. Those of you who've seen the schedule know why. Today's talk is the second and last theory-laden talk of the quarter, which is something of an anomaly. Today's speaker, Tim Roughgarden, is currently a Stanford professor who, while a grad student, noticed that systems with competitive actors were actually legitimate computer science. This shouldn't have been a surprising result, but it was, and he's got a great career out of the whole thing. And so much for the theory that computer science is a mature field. I mean, God, you just ran into a boulder. Thank you.
All right. Nice introduction. Yeah, well, they say luck is, opportunity meets something. So, I guess the lesson is for the graduate students out there, there's still kind of very juicy problems which no one has tackled. So keep an eye out. If you stumble on one, be sure to seize the opportunity. Okay, so I want to talk about algorithmic game theory. Thanks for the introduction and for the invitation. I wanted to use my time by giving you just sort of very brief and high-level introduction to a couple research themes more broadly in this field called algorithmic game theory, which is on the interface of computer science on the one hand, so it uses ideas from optimization, algorithm, and system design, and so on, but also it draws a lot on economics. So, for example, auction design, equilibrium analysis, and so on. So the field's only about 10 years old. I'm sorry?
It used to be
control theory, yeah. So actually it's interesting. So we're seeing new, so control theory and the economists are finally starting to get into control theory. And I'm actually very excited about that interface the next 10 years. It took a while, yeah, I agree. But I actually think we're going to see a lot in that direction in the next 10 years.
Cisco, by the way.
Say it again?
Cisco too, rediscovering control theory.
Yeah, perhaps, you're right. So, but they're talking to each other, so it's good. Okay, so algorithmic game theory emerged about 10 years ago as a field, and so why then? Well, I don't think it's an accident that in the late 90s is also when we saw sort of the widespread adoption and commercialization of the internet. So to anyone who's interested in sort of computer systems and interested in modeling, it was just obvious at that time that we started to have to seriously think about systems which had a bunch of autonomous decision makers with partially conflicting objectives. I mean, it was just clear that that was going to be everywhere. Obviously, auctions were there on the internet from the early days, of course, with eBay. Nowadays, sponsored search auctions, search engines like Google and Yahoo derive sort of most of their revenue from auctioning off part of the real estate of search engine pages via sponsored search auctions. But even beyond that, if you just think about the internet itself, you see competition and interesting strategic relationships everywhere. You have end users competing for scarce resources like network bandwidth. Internet service providers, of course, have a very complex strategic interaction. They need to cooperate to ensure mutual connectivity, but at the same time, many of them are sort of competing for customers in common markets. So everywhere you look in the internet, it's really rife with interesting sort of game theoretic interactions, and so it was clear that computer scientists were going to have to start getting economics and game theory involved. There are, of course, other branches of computer science that have been around a long time with autonomous decision makers, but in most, there are exceptions, but in most of those fields, notions of agent behavior were restricted to be one of two diametrically opposite things. People mostly focused on the extreme cases of obedient agents, which would just naively execute any instructions dictated to them by an algorithm or protocol without doing a cost-benefit analysis. Or if you wanted to be paranoid, you would worry about adversaries who you assumed that their only goal was to obstruct your sort of objective as a system or algorithm designer. Think, for example, about distributed computation. Usually you model non-faulty processors as obedient. Faulty processors are often modeled adversarially. You can think about cryptography, where you have the dichotomy between honest parties that follow the protocol and an adversary that wants to break your protocol. But if you look at what we're trying to model here, certainly something like an internet service provider will not be faithfully modeled labeled as either obedient or adversarial. It's not just going to do what I tell it to without thinking about the implications for it, nor is it going to say grind the internet to a halt because of the consequences for that internet service provider. So that sort of disconnect between the agent behavior models that people had at that time and the emerging applications kind of led to algorithmic game theory starting to be a field of its own about 10 years ago. Sorry for the shameless plug. Like I said, it didn't exist 10 years ago. Now there's several conferences and workshops every year devoted to the field. The first book came out in 2007. My co-editors are Noam Nissan from Hebrew University, Eva Tardos from Cornell, Vijay Vazirani from Georgia Tech. 800 pages, hardback, $45. Not that bad, but if that's too much for you, there's a non-printable PDF for free on my webpage. Okay, so obviously if there's anything, if you want to sort of get a broader sense of the field that I'm going to be able to give you today, feel free to check that out, okay? All right, so in the book, we sort of organized the research themes in algorithmic game theory loosely into 3 sub-areas. I've worked across all of these, as have, of course, many other people. I'm only going to have time to tell you about sort of 2 recent results in 2 out of the 3. So just at a high level, what are these? So the first topic I'm going to talk about is the idea of taking an engineering system, so I'm going to focus on large networks, and trying to view it usefully as an economic system, and thinking about steady states, thinking of it as if it was an equilibrium, and in particular the emphasis will be asking when can you have some kind of performance guarantee of steady states of large systems. So even though you have autonomous decision makers, you don't have direct control over their actions, your system's going to be at some steady state, can you actually have a meaningful comparison between that and what some all-powerful designer could achieve with full control over the system? Question?
Stepping right in the middle of one of the biggest problems in talking to economists and computer people at the same time. Which efficiency do you mean?
Okay.
Do you always mean software efficiency?
So I'm actually going to be looking at a routing problem, and I'm going to actually mean just delay of data passing through the communication network. So it's
software efficiency and not economic efficiency.
Oh, sorry. Oh, excuse me. What do I mean by actual efficiency?
There's 2
okay.
efficiencies.
Absolutely.
The 2 communities have very different models of what efficiency
I
is.
completely agree, and I literally rewire my brain depending on which community I'm talking to. I was assuming I was speaking to engineers here, and so I did not mean economic efficiency. I meant, and so in this case, efficient use of resources. I mean minimize delay. Yeah. So, yes, agreed. So that's what I mean. Thank you for the clarifying question. Okay, so it's going to be delay minimization. You can look at other objectives. I've looked at other objectives, so have other people. I'm just going to give you one example and talk. Okay, so I'll give you one very old result, actually, about analyzing performance guarantees for routing and traffic, and I'll also give you one sort of new result, an impressionistic version in any case. So the second sub-area is called mechanism design. Just think about that as auctions. That's really what it means for our purposes. Sponsored search auctions that we talked about is one special case. And here the challenge for the designer is really different. So in the first area where we're talking about large systems, the challenge for the designer is you wish you had more power. You wish you had the power to dictate how people used your system, and you don't. And that's why you in general will not have full optimality. In auctions, the challenge will be you lack information, you lack data. Okay, so there's an underlying optimization problem you'd like to solve, you'd like to make as much money as possible, you'd like to achieve, here's the other notion of the word, an efficient allocation of scarce resources, but you don't know how valuable these goods are to the participants. You just don't know that a priori. That's why you're bothering to run an auction. Okay, so you lack information in the second context, you lack power to dictate actions in the first. Okay, so I'll give you brief results in each of those. What I won't talk about is called the complexity of equilibria. There's plenty of that stuff in the book that I mentioned. So for example, how hard is it in a complexity theoretic sense to compute a Nash equilibrium of a game? Turns out there's interesting complexity theory. For example, NP completeness is the inappropriate notion of difficulty. You need a different concept called PPAD completeness for technical reasons, and you can see much more of that in the book. Okay? All right, so the theme to look for, so even though the 2 application domains I'm gonna talk about are quite different, the flavor of the results and what I want, so the kind of recommendation I want the theory to give is going to be similar in both. So it's going to be what's called in computer science competitive analysis, and so this is kind of bread and butter stuff in theoretical computer science, although the application in game theory situations is only new to the last 10 years. And the idea will always be we have some objective we want to optimize. So in the network context, we'll want to be minimizing delay of traffic. In the auction context, we're going to want to maximizing revenue. So there's some objective, and we will compare 2 different solutions under this objective function. And we're going to look at their ratio. On the one hand, we will have our protagonist, okay, something we want to prove guarantees about, which is also subject to quote-unquote realistic constraints. So in the network context, we're going to be looking at steady states of networks where we cannot, in fact, dictate routes to traffic. In the auction context, we're going to be looking at an auction which does not already know what people's value is for the goods. And we're going to make an unfair comparison. We're going to say, how well does our protagonist do when measured against some notion of an unattainable optimum, which will provide our yardstick. So in the network context, we'll say, let's do the thought experiment. What if we actually were all powerful and could control exactly how the network was used? How much better we could do? Surely we'd do at least a little bit better. A lot better? A little better? What? Okay, so that's what this ratio quantifies in that context. In the auction setting, we're going to say, what if in a parallel world, we actually knew much more information? We knew how people value these goods, or at least we had good statistics on how people value the goods we're trying to sell. Surely we could do better by how much? And the flavor of the results will be an interesting kind of guarantee, is if you can say your protagonist, subject to these real-world constraints, is actually almost as good as how well you could do with more power or with more knowledge. Okay, and that is a way of having a robust guarantee and saying a particular solution, a particular problem is a good solution. Okay, so that's going to be the flavor of both of the results that I talk about. So let me jump into the traffic networks. I'm not going to have a slide which has the full mathematical model. I'm just going to define it by example. I hope it's clear how it generalizes. If it doesn't, please stop me and let me know. Okay? So this is a very special case of the network model that the theorems are going to be about. This is a really old example talked about by Pigou in his 1920 book. He was an economist. And he phrased it in terms of road traffic, and maybe that's the easiest way to think about it. So, just imagine there's a large population of people driving from the suburbs to the city at roughly the same time, at rush hour. They all start at S, they all want to go to T. Okay, so there's a blob of traffic. Think of there being thousands of drivers, each one itself is individually small. They're all autonomous. They can pick either of these routes. Okay, that's totally free will, they can do what they want. And they want to get there as quickly as possible, as you'd expect. Okay? So the nature of these two routes are different. I'll let you sort of think of the analogy to the highways 101 and 280 if you like. There's a good connection. The black label on the bottom link, when I label it 1, what I mean is this is high capacity but long. The delay incurred by traffic on this link is 1, independent of the congestion. Okay, no matter how many people you have to share it with. The top link is short but gets congested. By the X, I mean if an X fraction of this traffic uses that top link, they all encounter X units of delay. So say X hours. 50% on top, it takes a half an hour. If all the traffic's on top, it takes a full hour. That's what the X means on top. Now, what did I say I wanted? I wanted to do a comparison between two things. What's going to really be there in steady state in the real world when these autonomous decision makers optimize their own objectives versus what I could attain if I was all powerful. So let's look at them in turn. So what would we expect sort of rational or selfish traffic to do? Well, if you were one of these drivers, this is actually a pretty easy decision to make. Right? So you say, well, the bottom link, in the best case, if it's empty, takes me an hour. The top link, in the worst case, if it's full, takes me an hour. Otherwise, it's better. Why would you ever take the bottom link? Okay? It's easy to formalize. The unique steady state for any sort of reasonable mathematical model has all selfish traffic routed on the top link. They all encounter a unit of delay. Okay? So average delay is 1. If you were all powerful, what would you do? And you were altruistic. You wanted to minimize average delay. You'd do anything but this. This is the worst thing. Okay? A calculation shows you would split them 50-50, actually, if you cared about average delay. You'd peel off 50% of the traffic from that bottom link. You'd reroute them from the top link, you'd reroute them on bottom. They're stuck with an hour, but that's what they had before. Those lucky ones who remain get there in only half an hour. Okay? On average, it's 45 minutes, 3/4. Okay? So the price of anarchy, when I say that word, what I mean is this competitive ratio between these two things. Okay, I look at the ratio of the steady state, in this case 1, versus what you could attain with full power, in this case 3/4. The ratio is 4/3. In other words, with full power, you could decrease the average delay by 25%. Or if you want to think about it the other way, by not being able to control people's actions, you lose 33% for the average delay metric. So the obvious generalization of this is you look at any old network, an arbitrary directed graph, you look at any old traffic matrix, these guys from point A to point B, these from point C to point D, and so on, and links have, more or less arbitrary, let's say, convex increasing functions or something like this, okay, on each link. So that's the general model. Any questions about that?
So if half the people are greedy, that's optimal?
Say it again.
If half the people are greedy, that's optimal.
If half the people, right. So, or if you like, so if half the people are willing to, be sacrificed to the bottom link, then you can have something which overall is optimal.
Biology might find that out.
Yeah,
that's
true.
why we have greedy.
You can talk about different implementations. I mean, in other ways, you could have a binding agreement up front where everybody flips a coin, and if you're lucky, you go on top. If you're unlucky, you go on the bottom, right? And then now individually, everybody has 3/4 on average. So you can talk about how to implement the optimum. I'm not even going to worry about that. I'm just going to say let's assume we're at steady state. And I'd still like to prove that we're pretty good. Okay? And in fact, if I could prove that in any network, no matter how general, you only had this 33% loss, in my opinion, that'd be pretty amazing, actually, right? So arbitrarily large complex networks, you let people do whatever they want, and you get some really quantifiable and pretty close to optimality. So unsurprisingly, guess what? That's not true. Let me show you why that's not true. And actually, let me rephrase it now in terms of communication networks, just to get you thinking about different interpretations of this model. So it's going to be it's the same trivial network, and it's going to be almost the same example. I'm just going to replace that linear function x by a really nonlinear one, x to the d. Okay, and then that's enough to sort of give us unbounded efficiency loss. The way I want you to maybe think about that is think about a communication network where delay comes from two sources: propagation delay, which doesn't depend on congestion, and then queuing delay, which does depend on congestion. So think of it, just think of it being an MM1 queue, say, on each link or something like this. It doesn't really matter what the model is for the qualitative results. Now, what's the analog of the 1 and x? Well, we should have one link corresponding to the 1, which has very big propagation delay. Okay, it goes really far, but it's really huge capacity, so you're just never going to see any congestion delay. You never see queuing effects. Okay, so that's going to be the 1. And then on the other hand, you have something with almost zero propagation delay, but it's small capacity, so you'll see congestion effects really quickly. By congestion effects, again, I'm not going to be overly formal, but this is my impressionistic drawing of an MM1 delay curve, 1 over the residual capacity. So that asymptote is meant to be the capacity of an edge, and we're looking as the traffic rate approaches the capacity from below, and it shoots off to infinity at the asymptote. Okay, so again, delay proportional to 1 over the residual capacity. Just to be, keep it the same as the last slide, let me approximate these two things by 1 and x to the d for d large. Okay, so that steep part, think of it as x to the 100. It's good enough for my purposes. Let's do the same thought experiment. What happens at steady state? What would the all-powerful designer do? The steady state is unchanged. Exactly the same reasoning. In the best case, the bottom link is 1. In the worst case, the top link is 1. Again, everybody would take the top link. The average delay remains 1. Of course, the all-powerful designer would still peel some traffic off. There's no need to peel off 50%. Let's just do, say, epsilon, where epsilon goes to 0 as d goes to infinity. Reroute this epsilon fraction on the bottom link. Now as d goes to infinity, or as you like, as you get close to capacity, the average delay is basically 0 over this dictatorial solution. Why? Almost everybody's on the top link, 99%. What's their delay? Well, it's 99% raised to the d, and if d is large, that gets powered down to like 0. There's a few martyrs stuck on the bottom, but they contribute nothing to the average, so who cares? Okay? Average delay, basically 0 in this all-powerful solution. So the ratio in particular is going to infinity as this network, as the capacity saturates. Okay? So sometimes you're good, sometimes you're bad. What would be a useful result for a theorist to prove? What would be a useful theorem? Well, in my opinion, what would be useful here would be to have a simple sufficient condition which effectively gives you a design principle and says, if you want to design a network so you're not in this bad case, so you look more like Pigu's example, so you have bounded efficiency loss, what should you do? What do the good networks look like? So that's the result I want to tell you about. And I think the design principle is something that will resonate with people who actually think about communication networks, which is that a little over-provisioning helps a lot for performance. Okay? And that can be made extremely precise and quantitative in this model. I'm going to do that by parameterizing on the extent beta to which a network is over-provisioned. Let me tell you what I mean by this. Okay? Basically, in a sentence, beta equal to something like 0.1 means max link utilization is 90%. Okay? So in other words, when I say beta is 0.1, what I mean is I'm thinking of a model where every link has a capacity, like in that graph with the asymptote of the capacity, and I want the residual capacity at steady state to be at least 10% if beta is 0.1.
Is this about throttling the traffic, or is this about making sure the capacity is 10% bigger than what you think the traffic is going to be?
So I would say both of those are legitimate interpretations. So if you want to start with a hard constraint that you want to allow a certain amount of traffic, it would say build the capacity 10% beyond the target, which would be enough under idealized conditions. If you're stuck with your capacity and you are able to throttle the traffic, it would say, back off by 10% and that's enough. Okay, so either way is a totally legitimate interpretation. Okay? So again, beta equals 0.1 means 90% max link utilization. Beta equals 0.01 would be max 99% link utilization, and so on. And I know this isn't really a theory seminar, but I'm still a theorist, so I feel compelled to give you some at least slightly non-trivial formula. There it is. 1/2 times quantity 1 plus 1 over square root of beta. All right? What does that mean? Let's get some feel for it. Let's look at the extreme values of beta. Let's take beta going down to 0. What does that mean? That means that at steady state, this network is nearing capacity. Right? So what happens to that expression? Well, beta's in the denominators. This is blowing up to infinity. We already knew that. I already showed you an example. As it approaches capacity, you get unbounded ratio. No surprise. Take beta going to 1. Again, we get something unsurprising, but at least reassuring. This goes to 1 as beta goes to 1. Remember what beta going to 1 means? It means you have essentially infinite capacity. It's arbitrarily over-provisioned. And routing should be trivial, and it is. You get a ratio of 1. What's so nice about having such a precise expression, and this is exactly the right answer, okay, so there's matching lower bound, so this is exactly the right dependence on beta, you can plug in a modest value of beta and see what you get. Let's plug in 0.1, 90% link utilization. And many real communication networks run a much lower than 90% link utilization, is my understanding. Plug in 0.1, and then the square root is something like 1/3, and so you take this average of the two things, you get 2. Okay? So over-provisioned by 10% only, and you drop from infinity to 2. And I want to emphasize this is a worst case bound. I also want to emphasize this is not just for that trivial 2-link network. Okay? So this upper bound holds, is valid for arbitrarily large and complex networks, for arbitrary traffic matrices. Okay? You can have different origins, different destinations, crisscrossing, I don't care. As long as it's over-provisioned in this sense, this upper bound will govern the worst case loss at steady state, at average delay of your network. Okay? So any questions about that?
You need the square root? Can you pick any root?
No, you need a square root. This is sharp for all values of beta. So basically, if you just play around with the 2-link example, you can match this for all values of beta. This is the right answer. No improvement possible. The one thing you could try and do is you could try and have a better average case analysis. And that, I think there's actually room for interesting work there. So you could say for most networks you do better than this worst case bound. But there's no such results known. Okay? But again, the point is, I think for actually extremely realistic and essentially already used rule of thumb, you get very tight bounds, even in the worst case. So you could argue why bother doing average case analysis if the worst case is already so good. Other questions about this? So this is the old result about routing I wanted to mention. I still want to briefly advertise a much newer result. Okay, so that was a special case of a result of mine that I proved back in 2002, which was a time when the price of anarchy landscape was much more barren. There were not many analyses out there. Since then, I've been pleased to see this blossom into really kind of a rich literature. Many, many people have tackled applications across electrical engineering, computer science, operations research, identify conditions under which equilibria are near optimal in similar senses. And so what I think a good sort of topic for this area to cover next is to try and get more robust guarantees in the following sense. So what do you know if the price of anarchy is bounded? You know that if your system's at equilibrium, then the performance is almost as good as if you had full power over the system. Okay? But let's look at that hypothesis. If your system is at equilibrium. Some systems naturally gravitate toward equilibria. For others, it's not so easy to actually be at a steady state. Okay, and we see that all the time in real life. And so what this next theorem is about, it's about weakening significantly the hypothesis that your system is at a steady state while actually getting just as good performance guarantee. Okay? So, of course I have to make some hypothesis about what's happening in your system. If it's in a totally arbitrary state, and it's a non-trivial system, I won't be able to say anything interesting. So I don't want to assume it's at equilibrium. I want something strictly weaker, but it still has to give me some bite. So here's an example. Okay, I should say that a lot of different generalizations work. I'm only going to show you one, but there are analogous theorems for many other generalizations. So we're now going to imagine a system not at a single state, but rather being played over time. And the interpretation is you should imagine a bunch of players, a bunch of drivers, say, groping, looking for an equilibrium. And maybe they never find one. But they're experimenting, trying to do the best thing in this system with changing, with the different drivers in different traffic patterns day after day. So a sequence, so think about 100 days in a row. We look at, so it's more general than just routing, but think about routing for concreteness. So think about a network. We look at day 1, we look at what routes people pick, call that S1. So S1 is a traffic pattern. We look at day 2, we look at what routes people pick. That's another traffic pattern, maybe very different. That's S2, and so on. So we get a sequence, one outcome, one traffic pattern for each day in the window that we're looking at. Now, the key definition is that of a no-regret sequence. Okay, so this is going to be a weakening of being at equilibrium. So a special case of a no-regret sequence will be you take a steady state and you play it over and over and over and over again. Okay, that will be a no-regret sequence, but here's the weaker definition. From each player's perspective, I want the following to be true. Okay, so in general, you tried a different route each day. You saw different delays. All of your competitors did different things also. I want at least the following minimal requirement to hold. It should not be the case that after you go back through the newspapers and look at the traffic reports, look at the traffic patterns on all of those days, there better not have been a single route from your origin to your destination that had you just non-adaptively used that single path over and over again for all 100 days, your average delay shouldn't have been strictly better than what you achieved with your presumably rather intelligent groping for an optimal path. Okay? So I'm asking that players are smart enough to be competitive with the best non-adaptive policy in hindsight. Okay? So again, I show you, right, so we run time for 100 days. I say, well, now I'm going to tell you what all your competitors did, but I make you pick the same path every single day. How well could you do? Okay, no regret means everybody did at least as well as the best non-adaptive strategy. Now, a priori, I shouldn't expect you to have intuition about whether this is easy or hard to attain. Okay, the one thing which I hope you see is that if you just play a steady state over and over and over again, you certainly have this no regret property, because you actually did a non-adaptive strategy and it was the best one given what everybody else did. But in fact, and this goes actually back to portfolio optimization, back in the 60s, Tom Cover actually worked on stuff like this and showed up in all kinds of different contexts, also Hanen back in the 50s. So for 50 years, we have known that very simple hedging strategies, which appropriately balance between exploration and exploitation, are guaranteed to achieve exactly this no regret property. Okay? No matter what the environment is, no matter what your competitors do. Okay? So if you're at least smart enough to either use an off-the-shelf simple hedging strategy, or maybe you do something much smarter and adaptive and better, that's great, but you're at least smart enough to get this no regret guarantee. So in contrast to equilibria, so equilibria, there's really two implicit assumptions when you say steady states at equilibrium. First of all, players are rational and know how to respond to their environment. And secondly, they coordinate. They manage to simultaneously reach a common equilibrium. Here we're making only the first assumption. Players are at least smart enough to get no regrets, but they do not necessarily ever converge. They do not coordinate on anything. And indeed, it's easy to find no regret sequences which are wildly oscillating among a bunch of different states, yet they're no regret. Okay? And again, many other definitions, many other weakenings are possible, but this is maybe my favorite. I'm not going to state this formally, but basically the takeaway of this new result says all of the most well-known price of anarchy analyses, including, for example, that 1/2, 1 plus 1 over root beta bound that I showed you, the way in which these upper bounds on equilibria have been proven means that the exact same quantitative bound extends without any degradation to all no regret sequences. Okay, so for n years, 7 or 8 years, we've been proving bounds on equilibria, thinking that being in equilibrium was a critical hypothesis. Okay, because the idea was, well, if you're in an arbitrary state, you can't prove anything, so you better be at equilibria. And the point is, no, actually, all of these bounds are far more robust than we realized. You do not need to coordinate on the common steady state. As long as you have the no regret property or various other analogs I'm not going to tell you about, you get exactly the same number. Okay, so in particular, again, even if you have non-steady state communication networks that are over-provisioned, you will still do well. Okay? Yeah?
So what does beta mean if I have this wildly changing?
So that would be the average. So you would look at the average traffic pattern.
What I don't understand is what keeps a link from getting saturated in some conditions?
Yeah, so some of the states may well be poor. Okay? So you're worried about that blowing everything up?
Yeah. You're saying if you increase every link by beta, then the effective throughput is this 1 over 1/2, 1 plus 1 over.
So I guess, the way to reconcile this is it's hard to satisfy the no regret property if you have certain outcomes where you're extremely saturated. That means there's going to be some highly costly things. So if there exists a way, if there exists a routing where you're backed off from the asymptotes, right? So the assumption is it's an over-provisioned network. So if you reached a steady state, it would be true you had 10% extra capacity everywhere. So that's the assumption. And now we're saying, what if you're not at a steady state? And I guess, the way to think about it is, what the proof basically shows is if you have a sequence, so this is the contrapositive, if you have a sequence so that you're pretty often close to the saturation point, it cannot be a no-regret sequence. Does that make sense? So perhaps I could rephrase your question as saying, well, maybe no regret is still too strong in a communication network. I think that would be a legitimate comment at this point. I mean, I'd love to weaken this even further, but that's the mathematical resolution of the paradox. Okay? All right, so this applies both for the routing as I told you, but also for many other applications. Okay, almost all the applications that people have actually thought about, with maybe one exception that are in the literature. Okay? So that's what I wanted to say on the first topic. Any questions about that? Yeah.
Just a quick comment. Is it equivalent to saying you want to avoid gridlock? Too simple a way of thinking about it.
So it kind of says if you see gridlock in a system with reasonably smart participants, then there does not exist even a centralized way of avoiding gridlock. It basically says you just have a low capacity network and you really need to add capacity. So again, I mean, so one thing to remember is, so we're doing these comparisons to what a all-powerful designer could obtain in this fixed network. So it leaves open the possibility that even the optimal solution is really crappy in this network. You're only good relative to this optimal solution. So that's the interpretation. If you see gridlock at steady state or in a no-regret situation, it means you'd even see gridlock with full control over all the routes.
You have greedy participants. What if you have griefing participants?
So the model is, so it depends a little bit on the model. The model I just showed you here is actually quite robust in many senses, including what you're talking about. So you mean what if players really want to harm the system? So I mean, if you assume that they can only harm the system by driving in particular ways, so it doesn't handle things, so totally outside the model would be if you somehow bring a link down. Okay, so that I'm not trying to model here.
You get 5 cars and you occupy 280.
Right. So this is relatively robust in the sense if you have an epsilon fraction of the traffic who are malicious, then these bounds degrade as a nice function of epsilon. You do not get any phase transitions. There are other applications which are more brittle. This one is actually quite robust, using the same kind of proof technology. Other questions? Before I switch gears. Okay. Good. So let me say a little bit about auctions and some work I've done here. And again, very different application domain, but you should be on the lookout for a very similar kind of result that I want, where I'm going to compare my protagonist, my solution to, in this case, someone who knows more. And I'd like to say that no matter what this missing knowledge is, my solution still performs well. So go ahead and think concretely about something like sponsored search auctions. That's fine for the purpose of this talk. So here, as I'm sure you all know, you type in camera, you get back your organic search links, and then you also get sponsored links over here on the right. And so obviously, so these are advertisers that filled out a form with Google that said, hey, if someone types in camera, if you show my link and someone clicks on it, I will happily pay you, say, 50 cents. Okay, so advertisers offline have input bids. Clearly, there's some automated auction, some algorithm which is figuring out exactly which links to show. In general, there's a lot of competition for this real estate, so there's many more people than you see who would be happy to be shown. And also, it's a little bit complicated, but the algorithm actually determines what the prices should be. And that's an interesting algorithm, which I won't have time to talk about, but it's pretty related to the stuff that I will talk about. So the results I'm going to tell you about apply to sponsored search. I'm going to specialize it a little bit to keep the notation down. I'm going to talk about the simpler case of multi-item auctions. And even for most of this talk, even go ahead and think of K being equal to 1, where you just want to sell one thing. So for example, I want to sell this laptop to somebody. But it's useful to have K copies of a good. So these would correspond to those K slots on the right-hand side of that web page if they were all the same. They're not all the same. People generally want top ones more than bottom ones, but ignore that for now. Again, the theory extends without any problems. So n bidders vie for K identical goods. So remember, nobody gets 2 goods, just like no advertiser gets 2 slots on a web page. And so now again, remember the challenge in auctions is different than in the large system context. Here we're missing data. We don't know the value of what we're selling to the buyers. Okay? If we knew that, we would not need to run an auction. We would just find the people who wanted it the most and get them to pay for it. Okay? So we want to know who values it the most. And we also want to get some semblance for what a fair selling price is. That is the point of the auction. How do we model that? Well, the standard first cut model is we imagine each bidder I doing a thought experiment and saying, what is my indifference point? Okay, so say it's for this laptop here, all right? So maybe, for 300 bucks, I would be indifferent. Okay, if I can get it for less than 300 bucks, I'd view that as a bargain, I'd take it. More than 300, no, I don't want that. Okay, so 300 is the threshold at which you would go from accepting it at that price to not accepting it at that price. That's called a valuation. This is what the auctioneer does not know. The bidder knows it, and it is not necessarily in the bidder's interest to have the auctioneer know this. Okay, so in particular, what do you do when you negotiate with something? Someone walks up and says, oh, I want to sell this to you. How much is it worth to you? Oh, I already got one of those, $5, right? And and you don't, you're lying about how much you're willing to pay. So there's clearly this game going on between the buyer and the seller, all right? And so thinking about that systematically is the domain of auction design. So an auction, it's just a protocol. It has to figure out which of these K at most bidders win. Remember, there's only K copies of the good, and what to charge them. Probably many of you, actually, let me do a quick poll. So how many of you know the second price or Vickery auction? Raise your hand. Okay. All right. I guess sort of the greater global worldwide audience can't raise their hand. So how about 50-50 in the room? Maybe let me just go through this quickly just so we're all on the same page. So think about K equal 1. Okay, so again, maybe there's 10 bidders vying for this laptop. I'm trying to sell off this laptop. So let's keep things simple, and this is more or less without loss of generality for my purposes. We're going to look at a sealed bid auction. Okay, so I take these 10 people and I say, write down in an envelope how much you'd be willing to pay for this laptop, and pass it over. Okay? Then they do this privately. I get the 10 envelopes. I open them up. I get these 10 numbers. I got to decide, what do I decide? Who wins? What do they pay? Right? Both answers probably seem obvious. Right? Who wins? Well, whoever said they wanted it the most, as they expressed by their bid. Right? So the winner should be the highest bidder. What should they pay? Well, if the person said they're willing to pay $230, cough it up. Write me a check. Right? $230. So that's a first price auction. It's used not always, but often in practice. It's a useful auction for many purposes. Right now I want to point out that is not the easiest auction to figure out how to play, what you should bid. It's not obvious. Say you are one of these 10 people. Okay? Say your indifference point is 300. Let me tell you what you would never write down in the envelope is 300. Why? It ensures you are all of a sudden indifferent to whether you win or lose. Right? If you win, you do so at a point where you have no net utility for that win. That's the definition of the indifference point. So surely you shade your bid, you try and get the laptop at a bargain. But of course, as you shade more and more, it is more likely in some sense that you will lose to one of your competitors. Okay? So that is the tension that you face. Now suppose you had X-ray vision and you could look in everyone else's envelopes. You can't, suppose you could. Right? If your indifference point is 300, there's two cases. One, somebody wrote something more than 300, in which case you say, too rich for my blood, you walk away. There's nothing you can do. If the highest other bid this is, say, 230, what would you write down in your envelope? Well, you'd write down 231. Okay? You would get it as cheaply as possible, subject to winning, subject to being the highest bid. Okay? But of course, you do not have X-ray vision. You make a guess, and that is how you play. That is how you bid in a first price auction. So Vickery had a cool question where he said, well, if we have an auction which in some sense is just as good, but where there's sort of a brain-dead way to play it. And there is. It's called the Vickery auction or the second price auction. And it's almost the same. He tweaks it in an interesting way. You again have the envelopes. You again have the winner be the highest bidder. But you do not charge the person what they wrote down in the envelope in general. Okay? If you wrote down 300 and your nearest competitor, okay, the second highest bid was 250, you will pay only 250. Okay? Why does this auction have the property that you should always just have a brain-dead strategy? Well, what is the brain-dead strategy? So the claim is the brain-dead strategy is just figure out your indifference point, write it down, tell it to the auctioneer. No matter what your model is of what your competitors are doing, no matter if they're crazy or rational, it doesn't matter. You will never regret doing this. Why? Well, how would you bid in a first price auction? What was the argument? If you had X-ray vision, you knew everyone else's bids, you would bid just high enough so that you would win. The auctioneer effectively has that X-ray vision. It collects the envelopes. It knows everyone else's bids. It is in a position to optimally shade your bid on your behalf, and that is the meaning of the second price. Okay? You're the highest bidder. You win. I look at everyone else. You would still win if I'd lowered it to 231 or 251 or whatever. So that's what I'll charge you. Okay? So are you just delegating authority to the auctioneer to optimally shade your bid on your behalf once it has full knowledge of all the other bids? So clearly that's good for you as a participant, independent of any model of what the other players are doing. Okay? Good. So what else did I want to say about the Vickery auction? So a variant, oh yeah, one other thing I wanted to say is, it's not that important for us, but it's good if you know this. It seems like you'd make more money for a first price auction, right? You're charging people more aggressively. What's obviously true is for a fixed set of bids, you will make more money in a first price auction because you'll charge the winner their bid, not the second highest bid. But participants, right, the mechanism is public, right? Everybody knows how eBay works, okay? Everyone knows roughly how these sponsored search auctions work. And what you bid is clearly a function of the announced auction. You will not bid the same number in a first price auction or a second price auction. You shade in a first price, you don't shade in a second price. And under sufficiently many conditions, which are sometimes satisfied, there's so-called revenue equivalence principles, which says, amazingly, these two phenomena exactly cancel out. Okay? So the extent to which it seems you would make more money in a first price auction is exactly offset by sophisticated bidders shading their bid appropriately. Okay, you get exactly the same money either way. So that's a sense in which the auctions I'm going to be talking about are more in the spirit of the Vickrey auction, where you have optimal foolproof strategies, but because of these revenue equivalence theorems, it's not an essential assumption. Okay, so these auction guarantees are going to be more generally for selling procedures, not just about those with these obvious optimal strategies. Okay, but focus on auctions like the Vickrey auction and a variant which is going to be useful for us, the Vickrey auction with a reserve price. So just think of this as one extra bid which is submitted by the seller. If I don't want to let the laptop go for less than $250, I'm just going to set a reserve at $250. Okay? There's a question?
Yeah, this assumes that the auctioneer doesn't lie.
Yeah.
Yes.
And just charge everybody what's in their envelope and say, that's what everybody else, that's where the price ended up, or shade it just a bit.
Well, yeah, I mean, either that they're honest or that it's verifiable somehow. That forces them. So either they're intrinsically honest or conditions are such that they're forced to be honest. Okay, so for example, if there's competition among multiple auctioneers and one has a better reputation for integrity, you would expect them to attract a better bidder set. Okay, but yeah, that's a little bit outside the model. It is an assumption, absolutely. Yeah.
Does it make any difference whether the reserve price is public?
As far as bidding behavior, so as far as how you should play in a Vickrey auction, you play the same way independent of the reserve. Yeah, so you should always just formulate your indifference point and pass that to the auctioneer. Now maybe your indifference point is below the reserve, in which case you may as well walk away. And so then if it was publicly announced, you would realize that. So at least at the level that at the course level of granularity, I'm going to be modeling things. It doesn't matter. But think of the reserve as public, as far as I'm concerned.
I just wonder why eBay doesn't make it public. Is it a psychological thing?
We have an option, actually. You can do it either way. Okay,
They
right.
want more bidders because it makes the item look more appealing.
Yeah, so it's actually a very interesting discussion, which I wish I had time for, to talk about eBay and the practice of selling reserves. I will. There's a guy, Kent Stieglitz, who's a Princeton professor, who wrote a really pretty book about sort of it's really pretty. He takes basically classical auction theory, including the stuff I'm talking about right now, and says to what extent is this correct for eBay and to what extent does it break down? And there's a lot of examples of both. It's called something Sharks and Shills. I forget now. Does anyone remember? Anyways, Kent Stieglitz. It's a really nice book.
By the way, he was a control theorist.
Is that right? He's also a complexity theorist. Yeah, and a control optimizer. So. Anyway, so he's an obsessive coin collector, it turns out. He is a radically more obsessive coin collector than I am a record collector, which is really saying something, believe me. So it's pretty amazing. Okay, so that's the reserve price. Okay, so just to be clear, so like if you have Vickrey with a reserve of 100, how does it work exactly? If no one clears the reserve, nobody wins. If two people clear the reserve, it's exactly like before. Highest one wins, second highest bid binds. And if exactly one person beats the reserve, they pay the reserve. Okay, so in other words, the winner pays the maximum of the reserve and the second highest bid. And there's an obvious analog when you have K. Okay, the max of the reserve and the K plus 1th highest bid. All right, so those are the kinds of auctions I want you to have in your head when I go through the next few slides. All right, so that's all just background. That's very classical stuff. So again, what would be useful for a theory to provide? So again, what would be useful would be some advice. I want to make money. What auction should I run? Or how should I set my reserve? Or any of these things. Okay, so how should I sell stuff on eBay? That would be useful for theory to provide. So it'd be nice to have some theorem of the following template. But you'd like to prove that some auction A is the best one. Okay, it gives you the most money, let's say. Okay, or at least almost, approximately. That'll be okay also. But there's sort of a problem, if you think about it, with theorems of this form. Okay, if you think a little bit harder. So let's just say I even wanted to rank two specific auctions, like the Vickery auction with no reserve and the Vickery auction with a reserve of $100. Which one's better?
Is this only from the point of view of the auctioneer?
Yeah.
Okay.
So is that a well-defined question?
I can give you the control theory stance. It says every scheme is optimal with respect to some metric.
Well, so I'm looking for almost that answer, which is every scheme, which, I mean, it's in the same spirit, every auction would be optimal with respect to some input. Okay? So the answer is it depends, right? So if you have an input where no one's willing to pay $100, obviously Vickery with a reserve of 100 is worse. You make nothing. Vickery would give you something. Okay? On the other hand, if exactly one person is willing to pay over 100 and everyone else is not, Vickery with that reserve does better. Okay, you make $100 instead of the second highest bid. So the answer is, it depends on exactly what it is you don't know. Right? So which auction you should prefer depends exactly on what people are willing to pay, which is exactly why you're running the auction. So what would it even mean? Okay, so I'm just pointing out there's an issue here. It's not clear what it would even mean to have a theorem of this form, to say that some auction is the best for all inputs or for a range of inputs. Yeah.
Isn't that the same result you get with voting systems? I mean, isn't that?
So you mean the possibility theorem, or? It is related. Yeah, I didn't think about it. I think this case might be a little too specific to derive from arrow, but it's a similar issue for sure. Okay, you sort of don't know preferences, and so it's not clear how to aggregate those preferences.
Well, and there's dozens of different voting schemes, and each of them is optimal given some set of voters.
Yeah, again, so here I'm talking about something which is more specific, it's more structured and less abstract. So it's not quite the domain where errors theorem usually operates, which is just abstract sort of rankings on outcomes. But I think the intuition is excellent. I mean, I think it's a similar tension that we're working with. So I think it's a very good comment. Okay, I already said that. All right, so the way we're going to do this is, and so the point is that competitive analysis gets around this, okay? So remember, what's the idea? We're not going to think about what's the best auction. We're going to envision a parallel world where we were just a smarter auctioneer, okay? And we could just do better. We could do better than any auction could reasonably attain. And if we can actually come up with an auction A with the property that on every input, and here an input is a valuation profile, okay, what everyone's indifference points are. If we could guarantee we could always get, say, a constant fraction of what a more knowledgeable auctioneer could attain, no matter what the input is, this would be an impressive, robust guarantee about an auction. Okay? We get some constant fraction of what we could do, even if we knew much more than we knew. All right, so could we possibly have, it's not clear that such theorems would exist. I just want to convince you, if we could come up with a single auction A, which had this property for every input, that would be interesting. Okay, that would be a vote for this auction. All right, where obviously the alpha, our loss, we want to be as small as possible. So then the question, all right, so that's fine. This is a little bit closer to a theorem, but I haven't defined our benchmark, opt of V. Okay, so if I told, so think of the following thought experiment. Suppose I actually told you how much everyone was willing to pay. Okay, suppose what number, what amount of revenue should you be impressed by? Okay, so if I tell you this auction makes $123 on this input, is that good? Is that high? Is that low? What? So certainly one thing that would be impressive is if you could get a constant fraction of the sum of the top K maximum willingnesses to pay. Okay, so remember, K is the number of items here, and VI is the willingness to pay. You know, at best, you identify the K people willing to pay the most, and at best, you get them to pay their maximum. No auction will ever do better than that, certainly. Okay? So if you could always get a constant fraction of that amount, you'd be golden. All right? So you can't. That is impossible. This is too, so this would be an omniscient competitor that actually fully knows what everyone's willing to pay, and that is just too much knowledge. Okay, so you can prove that every auction fails to compete with this strong benchmark. Okay, there's a bad input with respect to this for every single auction. So if we wanted a policy recommendation of which auction to use, this approach fails. Okay, it says all auctions are equally bad, which is not a helpful answer. That doesn't mean it's the right answer. It just means we have to reformulate our target, reformulate our notion of a more knowledgeable competitor. And so I'm going to give you the definition of that, although it's going to take a slide. I need to quickly a first detour into something which doesn't seem to answer the question. And then there'll be a theorem about why this does actually answer the question. So what I'm going to define on this slide is a smaller number. Okay, so remember we're trying to get a constant fraction of opt of V. And if we took opt of V to be the sum of the top K valuations, it's too big a number. We can't get a constant fraction of this. So this will be something smaller than some of the top K valuations. And to define it, think about the following thought experiment. Again, I award you full knowledge of everybody's VIs, of everybody's willingness to pay, but I don't let you price discriminate, okay? If this person's willing to pay 17 and this person's willing to pay 13, I don't let you approach them separately and say, hey, give me $17 for this item, and approach this other person and say, give me $13 for this item. You have to post a common selling price, and everybody who is willing to pay that price will get a good and pay it, even though it's possibly much less than their maximum, and anyone for whom it's too high will just not walk away with a good. Okay, so if you had valuations of 17, 13, and 12, and you were selling two goods, you could not sell for 17 and 13. You could sell for 13 and 13, that would get you 26. But if you sell for the top one at 17, it means everybody would have to pay 17, and you only sell one copy of the good at 17. Okay, so is that clear? So what I'm doing, compared to the auction, I do one thing which helps you and one thing which hobbles you. I give you the information that you want, what people are willing to pay, but I restrict you to post a single selling price which applies to everybody. Okay? So that's what this definition is. I mean, there's the math if you assume if the VIs are sorted. All right. So, okay. So why did people do this? So initially, this was done by Goldberg, Hartline, and Wright at the beginning of this century. They said, let's try to get a constant fraction of this number for every input. And the question is, why do this? And the implicit answer in the literature for 8 years has been, look, it works. What did we want from a benchmark? We wanted theorems that gave us advice about which auctions are good and which auctions are bad. And this seems to do the trick. What do I mean it seems to do the trick? Well, there's both positive results and negative results, and the revenue you could attain with an auction is in the same ballpark as this number, as this benchmark. So on the one hand, there's very cool randomized auctions that computer scientists developed in the early part of this decade, which guarantee you always get, say, 30% of this number for every single input. On the other hand, you can prove it's not an overly weak benchmark. It's impossible. There does not exist a solution which gets, say, 100% of this benchmark always, or even actually 40% of this benchmark always. So that's the sense in which it seems to be in the right ballpark. There are auctions which get a constant fraction, and you can't do better than a constant fraction. So fine, but I think a lot of people had the reaction, certainly I had the reaction, it just nagged me that it felt wrong. Okay, I didn't get this. It just seemed arbitrary. Why did it seem arbitrary? Well, it seems like an apples and oranges comparison with what we really care about. What do we really care about? We want to design an auction that maximizes revenue. Okay? In what way is the auction hobbled? It lacks information. It doesn't know the values. On the other hand, it can price everybody whatever it wants. Okay, and I want to emphasize this. The auctions that we're designing are not constrained to use a common selling price. And in fact, the auctions which satisfy this property that get within 30% of this benchmark do not obey this restriction, do not use a common selling price. Yet, what we're comparing to is more powerful in that it has more knowledge, but less powerful in that it's forced, artificially it seems, to use a common selling price. That's why this bothered me. Okay, it just seemed like we were comparing two things from two different worlds. Why should they have anything to do with each other? So the result I want to tell you about explains why they have something to do with each other. To explain it, let me do sort of one more thought experiment, and this is starting to get at what I mean by a more knowledgeable competitor. Okay, so we observe that if you're competing with someone who knows everything, knows the valuations exactly, it's hopeless. You cannot get a constant fraction of what they could get. What if they only knew statistics on what people were willing to pay? Okay, remember, our auction knows nothing at all. What if we give an opponent some statistics in the form of a distribution from which I promise those values will be drawn? Think, for simplicity, think about uniform 0-1. Let's even think about there being only like one bidder and one good. And we're just trying to figure out what price tag to write on this good before we place it in front of this bidder and say, take it or leave it. Okay, so maybe if it's uniform 0-1, you can imagine saying, okay, 50 cents. Okay, and you offer it to the person, and if their value is above 50 cents, then they take it, and if not, they leave it. Okay, and if they take it, they pay 50 cents. Okay? So this is, in principle, a super easy problem, right? So consider any possible, so I tell you the distribution, capital F is the CDF. Think about some possible price tag P. How much money do you make? Well, it's easy, right? Whenever the person accepts it, you make P amounts of dollars, and then there's some probability that they'll be willing to take it, because the probability the valuation exceeds P. So that's just this 1 minus capital F of P. All right, so for simple distributions, that's a simple closed form formula. You can just figure out what the optimal price is, what makes that as high as possible. Turns out for uniform, you actually would use a price tag of 50 cents. Okay? So this is an easy exercise. If I gave you statistics and there was only one bidder and only one good, what would you do? You would just maximize P times 1 minus F of P. A beautiful theorem of Roger Myerson, he just won the Nobel Prize for this and some other results last year in economics, says that actually, even as you scale K and N, there's a beautifully simple policy recommendation of what you should do, if you know statistics on the valuations. Suppose I promise you, and again, this is only a special case of Myerson's result, but in particular, his specializes to saying, suppose everybody's valuations are IID draws from this distribution capital F, okay? There's N possibly large number of bidders, there's K possibly large number of goods. The optimal auction, in the sense the auction that maximizes the average revenue you will make, the average is over the draws of the inputs, is exactly the Vickrey auction with a reserve price. Okay, so that's already very nice. It's a very simple auction. Okay, it's easily implementable. Even more remarkable is the reserve price is actually independent of K and N, the number of goods and the number of bidders. In particular, it's the same reserve you would use if K equals N equals 1. Okay? So in the uniform case, you would continue to use a price tag of 50 cents if you wanted it, in conjunction with a Vickrey auction, if you wanted to maximize revenue. Okay? I'm not claiming that's intuitive. Sometimes I proved this in my graduate class, but it's not trivial. Okay? I don't think it's particularly intuitive. I think it's a surprising result. Okay? So the upshot, what I want you to take away from this right now is that, our auctions know nothing about valuations. Our competitor who knows statistics is actually getting some very powerful information. Right? So if you tell our competitor, look, these are uniform draws from this distribution capital F, our competitor is going to say, well, I know exactly what to do. I'm going to run the Vickrey auction with a suitable reserve. Okay? All right. That's still not as powerful as knowing exactly what the sample point was, exactly what the valuations are, which was the first definition we tried. And it turns out, okay, so this is the result I want to mention, is that it turns out, and you can prove a theorem, so this is joint work with Jason Hartline, who's at Northwestern, is that what it actually means when you're competitive with this weird fixed price benchmark. So remember, this is where I tell you the valuations, but I constrain you to use the same selling price for everybody. What it actually means, so a consequence of getting 30% of that benchmark for every possible input, it actually means you're getting 30% of every imaginable opponent who is aware of statistics on the distribution. Okay, so it actually means you're simultaneously competing up to this 30% factor with every possible Bayesian optimal auction designer who is tailoring their auction to the distribution. So again, remember, we're designing an auction which knows nothing. Okay, it's just something like, I'm not going to tell you what it is, but it does not depend on the distribution. And we're comparing to somebody who does know a distribution. And even though they know the distribution and we don't, we get 30% of their revenue. Okay? So once again, what it really means to compete with that benchmark is simultaneous competition with all Bayesian optimal auctions. Just to make sure it's really clear, okay? So the way to think about this is, consider two possible worlds, okay? So you have to design your auction, you know nothing. On the other hand, your opponent is told this distribution capital F, and moreover, we evaluate both its revenue and our revenue with respect to IID draws. We're doing an average case analysis with respect to this distribution capital F, which again, our auction has no idea what it is. And the claim is for every capital F simultaneously, our average revenue with respect to this distribution will be at least 30% of our competitors' revenue with respect to that distribution, given that it uses the auction A sub F optimized exactly for that distribution. Okay? So not knowing statistics costs you at most this sort of 1 over 30% factor. Okay? Why could this possibly be true? I mean, you have to prove this, but sort of the one-line kind of glib intuition is that what does Myerson's theorem tell you? It tells you if you knew statistics, what you would actually use is Myerson with a reserve price. Sorry, Vickrey with a reserve price. And notice, what does Vickrey charge all the winners? It either charges all of them the reserve price, if there's not enough competition, or it charges all of them the K plus 1th highest bid, if there is enough competition. So in either case, the optimal auction on every sample point will actually use a common selling price. Okay? So there's some glue you have to fill in to get between Myerson's theorem and this theorem, but that's the idea. It turns out, if you knew statistics, the optimal auction would indeed use a common selling price on every single sample point. Okay? So any questions about that? I'm almost out of time, but any questions? Say it again?
But as a buyer, why would I choose an auctioneer who is pursuing an optimal revenue maximization strategy over an auctioneer who, for some stupid reason, chooses a less optimal?
So this is a good question. So
He'll still be in business next week.
Well, I mean, good luck to all the buyers. he takes less money, gets all the buyers, and the first guy loses.
It's still go out of business, even if you have all the buyers.
No, he just has to make money. He has to be over his average cost.
So I think what's interesting to think about is revenue is not the only objective that one might care about. And it's not even the one which is very explicitly optimized, say, by search engine auction setup. So those are based, so for example, the Victory auction, if you wanted to optimize, if you wanted the best allocation of scarce resources, you would have zero reserve. Because what does the Victory auction do? It solves an interesting problem. Okay, you have all these people, if you sort of measure sort of welfare to society based on the valuations of who actually wins, right? Even just say sort of there's one good. Okay, so basically what you have is you have a bunch of agents, they privately have numbers, and the optimal welfare maximizing solution would be to identify the person with the max number. Okay, so the Victory auction can be viewed as an interesting protocol to solve a computational problem. It computes the max of these n numbers distributed among agents who are selfish, who are not necessarily interested in telling you that they're not the maximum, for example. Okay, so the point being is, if you wanted to, so this is an interesting objective to solve, welfare, and the Victory auction solves it with no reserve. And so an interesting question is, under what conditions is Meyerson's theory relevant? And it's relevant, in my opinion, when you have enough market share. So if you have a seller with sufficient market share, then you can start getting away with revenue maximization. It's interesting to try and interpret this in terms of search engines right now and thinking about Google's market share versus its competitors. And they're not necessarily so transparent about the reserve prices they use. They are using reserve prices, although they're lower than what Meyerson's theory would predict. And so it's interesting to speculate, that there's still sort of enough competition among the search engine market. You have to use an auction which looks more like an efficient auction, a welfare maximizing auction, as opposed to a Meyerson revenue optimizing one. That said, reserve prices, like I said, do show up in search engine auctions used today. So, I think the prediction of a reserve is a pretty robust prediction. The exact numbers you get out of Meyerson is definitely dependent on a monopoly assumption. So Meyerson was thinking about a monopolist. That's exactly what his perspective was.
Can you estimate what they want as reserves?
That's exactly the flavor of the auctions that you can prove these 30% for. So basically you collect some statistics, and so even if they're not drawn from a distribution, you can pretend as if they were samples from a distribution. And then you can start using analogs of Meyerson solutions to do something on the people you didn't collect statistics on. So that's exactly the flavor of it. It's a lot of work to prove that they actually work, but that basic intuition is kosher. Okay? All right, so I'm not going to talk about this, but it turns out just to be the tip of the iceberg. This was sort of a reinterpretation of existing rules for multi-item auctions. So Jason and I are in the process of working on a much more general theory for much more harder problems. A killer application we'd really like to push the theory to, we're not there yet, although we're making progress, would be combinatorial auctions. Okay, so this is something much more general than multi-item auctions. This is where, in general, you have a bunch of goods, and remember, in multi-item auctions, someone either won or lost. Okay, all the goods were interchangeable, you either got one or you didn't. If you think about, say, the FCC auctions that you hear about which sell off wireless spectrum, all licenses are not the same. All licenses are not, some of them are substitutes, some of them are complements. You could easily imagine a provider would want a bunch of licenses very close to each other, right? So if you get just a few scattered small licenses, one in Northern California, one in Southern California, not so useful. If you get a cluster that's a big region together, pretty useful. Okay, so that's a very different flavor than the kind of multi-item auctions we've been talking about. And that would be the holy grail of this last line of research. I guess that would be the killer application of where this could go. So just to sort of finish up and just sort of remind you what the first half of the talk was about. So we were talking about bounds on efficiency loss in systems. And one interpretation, the last result I showed you basically says dynamics don't matter. In the sense that if you look at a game played over time, it doesn't even matter if you converge. Right? As long as you have something like a no regret property, that's good enough to get the equilibrium guarantees. Nevertheless, I still think there's some very interesting work to be done understanding the dependencies between the way a game is played and the results, say the steady state that you wind up at. Many systems have multiple equilibria. Some of those equilibria can be much better than others. What micro aspects of the way in which the game is played influence which of those equilibria do you wind up at, and how does that affect efficiency loss at steady state? So those are a couple open questions. I think I'm out of time, so let me stop there. Thanks a lot.
The camera example is sort of interesting because there's only 3 camera stores in New York City. Mm-hmm. They just have a bunch of storefronts. Mm-hmm. So in that sense, they're all auctioning against each other. There's only 3 players in some sense. more slots than players.
So you're thinking about, I see, so you're thinking about sort of each store as an expression of,
Yeah, it's odd. It's just cameras that are, I think cameras are the only one that are, it's that.
It's also interesting because the auctions are in competition with one another for bidders.
right, yeah, so the interplay between different search engines is clearly important, and the theory is quite weak at the moment about that. I think that's an excellent point, yeah.
I like the combinatorial auctions. Spectrum in particular is a case where the FCC, I think, isn't revenue maximizing when you want to allocate the spectrum.
Yes and no.
They say they want to
I mean, so it's fine, and I, to some extent I agree with that, but I mean, even if that's your goal, there's different implementations which seem to have very different revenue properties. And certainly there were some instances, I think New Zealand was one, where the auction was simply designed poorly, and literally they made in the tens of thousands instead of in the millions or tens of millions. I mean, it's made at orders of magnitude different. And similarly,
There's also a case with Google where there was some openness requirement that would only be applicable if some amount of revenue was made, and so Google put in a bid that ensured that the goods would only be allocated if.
right.
That alone distorted the auction greatly.
Oh, absolutely.
And I think, I mean,
That was the goal.
yeah.
Yeah.
So the interesting point there is sort of, a lot of the context of the auction can also be important. So I mean, if you're really, so I mean, it's funny how little reuse of specifics you see between different computational auctions. I mean, sort of like the underpinning principles, get reused over and over again, but the details are critical. And every time a new country does a spectrum auction, it's really a couple of years of work for professional, economists. I mean, there's a lot of devil in the details with those things.
Let's talk about opening up the electricity market in California 8 years ago.
Yeah.
It's a new design problem, and the economists all got together, and the politicians ignored them. Let's do something that's wrong.
I mean, I think when you look at the variance in the revenue made in different spectrum auctions, I think governments are actually pretty happy to have advice on it at this point. Because again, there were some big early failures and some big early successes. Again, there were versions where people made literally 100 times more revenue. I think England or Britain was one example. They made 2 orders of magnitude more than they were necessarily expecting. So yeah, I mean, so that's definitely the subject for a whole course, computational auctions, for sure. So.
Network routing also quickly falls into combinatorial auctions because you need pieces of links in order to make a circuit.
Right, that's right. So I'd say the big difference between the two parts of the talk was not so much in the combinatorial structure, where I agree the parallel is pretty strong, but again, more the way in which the designer was hobbled. So in the auction setting, again, the key challenge was this lack of information. And in the routing problem, that kind of didn't really come up. There wasn't any kind of preferences you were trying to elicit. It was a very simplistic model of user behavior. You just have this traffic, they're there, they want short paths. There's nothing to discover about them. So I think that's the main compare and contrast between the two. Is it really an informational problem, or is it more a kind of inability to directly allocate resources? And again, to further the contrast, notice in the spectrum auctions, there's no issue about who is assigning the resources, right? I mean, the government has them all and can split them up however it wants, and it chooses the auction about how to do that resource allocation. But I agree. I mean, so very often very similar optimization theory is useful in both of these contexts. So it's surprising how much mathematical commonalities there are sometimes, despite the fact conceptually the challenges are very different. That's a good comment. So.
This is roughly the same result that Carlin got with respect to online and offline cache control.
This is Anna Carlin?
Anna Carlin, yeah.
Okay.
You could do within a fact, if you knew all the
Right.
requests in advance
Right.
versus doing this.
Exactly. So I said this extremely briefly, but just back when I said a theme will be competitive analysis.
Yeah.
This is literally when you get a theoretical computer scientist like Anna or myself, and you give them something like this, our Pavlovian response is competitive analysis.
But it's
And
interesting,
so,
the numbers are all 2 plus or minus 1.
Yeah.
Or
Well,
3 plus or minus 1, but yeah.
I mean, if it gets bigger than that, we feel a little embarrassed. We start thinking it's maybe not such a good result. So. No, yeah, I completely agree with you, actually.
Is it study bias that if it's 5, you say, oh, well, I'm doing something else?
Well, it kind of depends, but I mean, like I said, the closer to 1, the better. So, yeah. But I agree. You see weird. There's certain numbers you see bizarrely often. 2 is one of them. 4/3 is another one. And, other questions?
I've been curious what steaming algorithms are.
Streaming? Oh, wow. That is
I tried
fun.
to point it out to you, but I
Yeah, well,
figured it was.
We also spell multi in an interesting way in a couple places.
Okay, sorry.
All right, forgive the typo.
Yeah. And this is one where the spell checker won't alert you, so it's kind of fun. Yeah, it's supposed to be streaming algorithms.
It seems so anachronistic as hoping it's really exciting.
Oh, yeah, that's funny. Yeah, no, so it's things where you kind of have to go over a large piece of data in one pass, and you have small working memory. And so suppose I give you a whole bunch of numbers, and you want to compute the median, but I only give you kind of a small amount of cache space. So you can't actually sort of do a brute force median computation. So.
Steam smells like physics. Have you looked into information physics? I got over into that, so did you have a look at all?
What would be the potential connection?
One naive way of thinking about it, all these distributions, unknowns, whatever. It's basically quantum information has some tools that may be a little more powerful to deal with some of these uncertainties.
Could be.
The fun part is that Stiglitz actually showed that basically quantum mechanics can be done with PEs. From a classical point of view, although his proof is that he admits it's epsilon close to the real proof. So it's not clear that's really the case, but it would be fun.
Okay.
And at that point, basically, forget about the quantum part, but basically some more sophisticated models in terms of uncertainty might help.
Yeah, I mean, so what you're saying is a bit outside my expertise, but I mean, perhaps along similar lines.
At some point, you may want to look into it.
Right. And more generally, I'd say, in this auction stuff, there's a flavor of learning an unknown distribution, which is clearly a very classical problem. It's been studied from a lot of different ways. And I think there are useful connections that have not been discovered.
Well, there's a weird one since in computer science here. Once you bring in quantum and topology and all this stuff, you suddenly start to get into Turing completeness. Maybe you do math actually, maybe Turing complete in the first place.
Aha, I see.
And then that might explain why you have this complexity and why stationarity is not an issue, and why in real time, basically what Cover said, there are real-time strategies that essentially do as well as if you would have known the whole future.
Right.
And think of that as a computing process.
Right.
Now, if you somehow have Turing completeness somewhere snuck in underneath through physics and statistics, to me that wouldn't be too surprising. Like evolution, if you actually look at the whole DNA story, is Turing complete. So it's a computing process. At that point, it wouldn't surprise you that
That's doing as
that
well
kind
as
of
other
complexity
things.
story going, and not to speak of it. I'm not surprised that people like you are looking at it.
Yeah, it's interesting. I really don't know.
Anyway, so there's a lot of stuff in there. Yes, you can kill yourself on it, but you may want to look at it.
Okay.
At least some parts of it.
Okay.
Okay?
All right, thanks very much.
For more, please visit us at stanford.edu.